Contest number 1, which is about compensating for a particular curve from the earphone buds that I did some measurements on. So just to kind of get you oriented towards this, we'll do a little graph, and we had something like that for the response curve. We're talking about frequency on this axis and magnitude on this axis. And what's important about this is that the frequency is in log of frequency, and the magnitude is in dB, which is another form of log. So we would typically have things like 10, 20, 30 dB on this scale, and the scales on this way, we'd say 10, 100, 1,000, 10,000 equally spaced hertz. And what we'd ideally like is the response to be basically flat, which it's totally not at this particular point. But there's things we can do to this by applying a number of filters to the signal as it emerges and make it virtually flat. So, for instance, when we see a part that's not flat, like for instance this part right here, we can say, oh, okay, approximated a straight line. I could say, well, what's the slope of this line? And I'm looking for some sort of slope in terms of, for instance, decibels per decade, like between 100 and 1,000, roughly speaking. What is the slope of that thing? And what I want to do is I want to apply a filter that's going to cancel out that decline. And so basically I'd be trying to produce a filter, let's say for this particular case, a filter that would start rising at a point in frequency that will basically cancel out the fall. This, which is the original signal, times this signal, is going to produce a flat signal over that range, because in dB, when you cascade two filters, like that, the gain at any particular frequency in this one, in dB, gets added to the gain at that same frequency of this one to produce the overall result. If I'm rising in my filter here at the same rate that it's falling in the original signal, then they'll cancel each other out and I'll get a flat response. And then I can cascade more filters, like this filter here. I can also do a filter over here where I say, okay, this guy is falling at a certain rate, and I'm going to apply a filter which has a response that rises at the opposite rate, and once again reinforces a flat response in this particular direction. And so I'd add another stage. You don't want to go nuts and try to completely match this curve. It's just not worth the effort by any means. Probably want to do a few stages, look at the major changes in curve and try to balance that out. One of the things you should be aware of is that when we design a particular filter, it's usually done with capacitors and resistors in some sort of combination. Let me take this off. And the response, let's say for a low-pass filter, is going to have some value, some gain value, over a term something like this. You can usually manipulate it in that particular form. B would typically be a very small number, and as your frequency in S rises, this overall term is probably pretty small relative to 1, and so as it changes, This is normally a constant. But once we get to the point, the particular frequency where B times S is equal to 1, and we get beyond that, then this amplitude starts to decline. And for a single pole, a pole right there, we would normally say that this declines at a rate of 20 dB per decade in the fall-off point. So this is the flat part, here's the decline. We would measure this and we say minus 20 dB per decade. And by decade we mean some frequency relative to 10 times that frequency. That's a decade fall. It could be 100 Hertz to 1,000 Hertz. It could be 5 Hertz to 50 Hertz. It's all a decade. So that's what we're looking. The reason that we measured, to bring this back for a second, the reason that we measure the slope at different points is we're going to approximate that slope in our filter by some multiple of 20 dB per decade. Maybe it's 40 dB per decade, maybe it's 60 dB per decade. In this particular design, we're using op-amp designs, and the question is, how do we design an op-amp circuit that acts as a low-pass filter for this kind of behavior, or as a high-pass filter for this type of behavior? And the answer is, we typically look it up in an application note. There's lots of design tips out there. In particular, if you go to the website of National Semiconductor, which is one of the leading producers of integrated circuits, analog integrated circuits in particular, their website of national.com has all sorts of information, and in particular, do a search for a particular application note, which are these little documents that these companies write to encourage you to use certain parts of theirs. And a real nice one, which is sort of a beginning one, is application note 72. It's written a long time ago, but it's got a whole bunch of basic op-amp circuits in it, and for a number of them, enough analysis that it tells you how to design, how to pick resistance values and stuff like that. In particular, it has a two-pole low-pass filter, which is very nice to give you all the design equations for it. They also give you a circuit for a two-pole high-pass filter. By cascading these guys together, you can start to approximate the type of behavior that you're looking for your particular circuit. So let's suppose that I'm trying to compensate the frequency response that I gave you for those Bud earphones, and just as an approximation, we'll say that the shape was something like this. That's very rough. In order to compensate for this, I'd like to get a circuit whose overall frequency response is basically the inverse of this. And I'm going to draw it as a series of straight lines as an approximation. So I'd say, well, to compensate for this, let's say I'm going to have something that goes like this. It's going to rise in frequency to about here. It's going to flatten out. That corresponds to a fairly flat period here. And then it's going to rise up again to compensate for this fall. Same thing on the other side. It's going to rise up, flatten out briefly, and then rise up again like that. And you'd have to measure the actual slope of this original line to approximate what multiple of 20 dB per decade rise or fall you'd have for this. Now, to achieve this, I'm going to cascade a bunch of parts together. So first of all, let's start from some point really low frequency, anything below 20 dB or 20 Hertz. Sorry, well, we can't hear anyhow. I'm going to say the first stage is going to be just a low pass filter that has a response like that, whose frequency is below 20 hertz, something like that. So that's my first stage. I'm going to follow that by a place where it flattens out. And in order to make this flatten out, I have to cascade it with another stage, which is going to have a response that has to cancel this particular fall with a rise of its own. The rise here cancels the fall there, put them together. If this is less than 20 hertz and this is, let's say, at about 80 hertz, for instance, then I'd say, yeah, at 80 hertz I want to rise up, cascade this one, followed by this one, to end up with something that falls and then flattens out shortly, as this does. Oops, this 80 hertz should be over here. Then a little bit later, at maybe 100 hertz, I want to start falling again. And so this guy plus this guy plus another low-pass filter, looks like it might be about the same slope as the first one, but at a higher frequency, at about 100 hertz. And then I'd have to go completely flat at this point, so I need to follow it by another circle like that. Each of these is different frequency. I choose the frequencies to either cancel for a period, or to start a new fall, or to once again to produce this, and so forth until I get all of the different sections of this put together. Each one of these would be represented by an op-amp circuit, and one op-amp circuit falls out. And look up for each of these stages. In, as I said, like the application note 72, you go online and just do a Google search for something like filter design or op-amp filter design, and you'll get lots of different sites that will help you with that.